Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. Gauss studied sums of squares by looking at factorization theory in his ring of Gaussian integers. And Lemay thought that he could also similarly study sums of pth powers and hence study Fermat's last theorem by using a similar trick. Unfortunately, there was a fatal flaw that was discovered by Kummer, and that's to do with the fact that you don't always have unique factorization. And what I want to show you in this video is how Kummer came to the rescue by introducing his ideal numbers, which became the theory of ideals that you see in abstract ring theory. Okay, so let's look at Lemay's attempt to prove Fermat's last theorem, at least the part that's going to interest us. Okay, so for that we'll fix some prime p greater than 2. And we consider the integral equation here, z to the p equals x to the p plus y to the p, and you can assume z, x, and y, there's no common factor in those three integers. Okay, so if you want to mimic what Gauss did for sums of squares, what you do is you factorize this, and you can do this, okay, if you join zeta, which is a primitive pth root of 1, okay. So that's what Lemay did. He did that, and then it nicely factorizes as follows. As you can see here, x plus y times x plus zeta y all the way down to x plus zeta to the p minus 1y. Okay, and so he did some arguments with this. So working on this, the key step was to show that, or one of the key steps was to show that each of these factors is relatively prime. And if each of these factors is relatively prime, okay, he argued that since this is the pth power, each of these factors should be pth powers as well. Okay, so that's what he said. And then he was saying, well, if these are each pth powers, then that allows you to do some further analysis, okay? That gives you a strong information and allows you to do further analysis to get his contradiction. And the problem was, of course, if you want to make that conclusion, what you need is unique factorization, okay? Since this is a pth power, okay, and these are relatively prime, okay, then each of these are individually also pth powers. That requires unique factorization. So the problem was that Kummer realized that it's not necessarily true that if you adjoin zeta to the integers, and that's the ring of integers, okay, in this number field, okay, the associated number field where you join this to Q, you'll get a unique factorization domain. So what did Kummer do to try to rescue this proof? And in fact, he managed to rescue enough of it so he could prove it for certain primes. Okay, so let me just give you the key idea of what's involved here by looking at a simple example. And the simple example is the following quadratic field extension. K equals Q adjoin the square root of minus 5. Okay, so this here, square root of minus 5. When you look at this, the ring of integers here, I want to write is Z adjoins square root of minus 5 here. Okay, and so what you have a following norm map. So you look at this norm map here, and what do you see? So in this norm map, you will see that if x and y are integers, so this is an element inside this OK. What does it map to? So it just maps to the square modulus. So it's x squared plus 5y squared. Okay, and even here you'll find already that in this ring here, this does not have unique factorization. And so why is that the case? So if you look at 6, of course, you can factorize it as 2 times 3. But actually, since you've adjoined square root of minus 5, you can also factorize this as 1 plus the square root of minus 5 times 1 minus the square root of minus 5. So here you have two different factorizations, and I claim that this 2 and these 3 are already irreducible. So since they're irreducible, and the only units that you have here are plus and minus 1, that means that this is not a unique factorization domain. Okay, so let's just check irreducibility, and we just use the norm to do that quite easily. Okay, so that's something rather nice. So here, suppose you can factorize it 2 equals a times b, where a and b are neither of them are units. Okay, and then remember the norm is multiplicative. Okay, so that means the norm of 2, so that's just the square of 2 is 4. Okay, 4 equals the norm of 2 equals also norm of a times norm of b. Okay, so you have the product of those two norms. Now, if the norm of a is equal to 1, that gives you a unit. Okay, the only possible solution is x equals plus or minus 1 and y equals 0, so that's a unit. So this factorization, if this is a non-trivial factorization here, that means the norm of a and the norm of b are both equal to 2. but you'll note that there are no integers in this ring here, okay, no elements of this ring whose norm is equal to 2. Because if you look at this, what solutions are this norm equal to 2 for integers? Okay, there are no solutions, okay, because that means that y has to be 0. Okay, this is a multiple of 5, so this has to be 0. And this means that x has no integer solutions. The square root of 2 is not an integer. Okay, so 2 is irreducible. And the same argument, if you put 3 in here instead, okay, you'll get a 9 here. And then if you want to factorize 3 as a times b, that means that you'll need some elements, a and b, whose norms are equal to 3. But again, you can't get that. So that means 3 is also irreducible. And so that tells you that this z adjoining the square root of -5 is not a unique factorization domain. Okay, so what was Kummer's genius? The Kummer's genius was to use ideals. He called them ideal numbers. That's where the name ideal comes from. And but we know what they are in ring theory now. Okay, so let me just remind you some basic definitions here. If you have commutative rings, a commutative ring R, and you have ideals I and J inside R, remember we can define the product IJ. Okay, the product IJ is going to be, you look at all the products of elements inside I, so AI inside I and BI inside J, okay, and you look at all sums of such products. And it's quite easy to see that this is itself an ideal inside R. So you get a new ideal this way. That's the multiplication of these two. And then P inside R is said to be prime if, when you look at the quotient ring R mod P, this is a domain. Okay, so you can work out slowly what that means, and it'll mean one thing. I'll formulate a slightly different way of saying this that hopefully you would have seen before, but it's quite easy to see that the two conditions here to be prime are the same. If IJ is contained inside P, okay, then either I or J is contained inside P. So remember, the way divisibility gets translated in the language of ideals is via containment. Okay, so in other words, J is contained inside P. Okay, that essentially means that you're thinking of this as saying P divides J. And if these are actually principal ideals, okay, that's what it means. It's divisibility of the generators, but in the opposite direction. Okay, so if you look at this definition and you use it just for principal ideals, you're basically saying is that if you have some a prime number, okay, and it divides a product, okay, then it has to divide one of the factors. Okay, that's what it means. Okay, so this fact that this prime contains means it divides. Okay, so if this divides a product, it divides one of the factors. Okay, so it's very much like the usual definition that you see of primes. Okay, so let's have a look at this ring here and these this 3 and this 2, but rather not as elements, but as the ideals generated by them. So let's look at the ideal 3. Well, the point is that this ideal 3 is not prime. Okay, but it is contained inside 2 primes. The first one is the prime that's generated by 2 elements, 3 and 1 plus root -5. We've called that P plus. And another one which is P minus, which is 3 generated by 3 and 1 minus square root of -5. Okay, so it's contained in these 2. It's clearly contained in those 2. And this is the symbol which means the ideal generated by these 2 elements. Okay, so basically the sum of all multiples inside here of these 2 elements. Okay, and further, if you multiply these 2 together, P plus times P minus, that's their 2 ideals that you can multiply together, you get this ideal generated by 3. So in other words, this 3 is not prime. Okay, okay, so 3, it's irreducible, but if you go to the ideals, in the setting of ideals, then you can factor it. So it's no longer irreducible in this sense. Okay, it's reducible in the sense that you can write it as a product of primes. And these primes, they don't correspond to units because the ideal generated by the unit is of course the whole ring. And these are actually maximal ideals. Okay, so these primes here are actually maximal ideals. Okay, so let me just show you why, and I'll use a fair bit of ring theory to actually show you so that you can really see how useful ring theory is to study number theory. Okay, so firstly, we want to look at the quotient, and I want to say that this is not a domain. And in fact, we'll say more about exactly what it is, okay? So you have a z adjoins square root of minus 5 modulo this ideal generated by 3. And one way to think about this, the easiest way to think about this, is to actually go modulo 3 first. You factor out by 3, so if you have z mod 3, that's just a field with 3 elements. And what you want to do with that is you want to join a square root of minus 5. Okay, so that's what you want to do, join a square root of minus 5. So once you're inside F3, remember, if you want to join a square root of minus 5, but what is minus 5 inside F3? So modulo 3, minus 5 is just equal to 1. So you just want to join a square root of 1 in this sense. It's F3, you join the x, and x is a square root of 1 in the sense that you're going to mod out by x squared minus 1. And the point is x squared minus 1, well, you can factorize this inside F3, okay, into two different factors. Okay, they're 1 and minus 1 inside here. So now you can use the Chinese remainder theorem. Okay, so this is the key point. You're going to use the Chinese remainder theorem here. So you get this as f of 3x minus x minus modulo x minus 1, that ideal, cross f3x modulo x plus 1. Okay, so you factored this ideal, okay, into a product of maximal ideals here. Okay, so that's what you have. And what are these each? Well, if you look at these as rings, what are they? Well, here you're basically setting x equal to 1. Okay, so you can forget adjoining anything. So you just have F3 here, and similarly you get a copy of F3. So this quotient ring is not a domain. In fact, it's a product of two copies of F3. So this one here is isomorphic to F3, and so is the other one. And so it has 0 divisor. For example, you can have 1, 0. That's an element inside here. And if you multiply that with 0, 1, their product is 0. So it's not a domain. Okay, and that tells you precisely what's going on. Okay. On the other hand, since you have this product, each of these will give you an ideal. Okay, so if you look at x minus 1, that will give you a maximal ideal. And if you look at x plus 1, that principal ideal generated that will give you the other maximal ideal. So what are those maximal ideals? Okay, so you've modded out by 3 already in here. And then if you let x equal 1, okay, x was the square root of minus 1. So x minus 1 means square root of minus 1 minus 1. Okay, so that means you might as well just adjoin that negative 1 minus square root of negative 5. So that's essentially the p minus. And the other maximal ideal is x plus 1. So that's the one where you have p plus instead. Okay, so that's rather nice that from this argument, okay, you can kind of read off what are the maximal ideals containing this 3. And they basically, well, of course, you have the 3 in there, but the extra things that you need to add, okay, before you just mod it out by x squared minus 1, okay, now you need x minus 1 and x plus 1. So you need a little bit more, and that corresponds to 1 plus square root minus 5 and 1 minus square root of minus 5. Okay, so the other thing that you should know that those are maximal ideals when you factor them out. So p plus and minus, they're actually maximal. And when you mod up by those maximal ideals, you get F3 in either case. So you'll get a field, so that's actually a maximal, and particular domains, so they're prime. So p plus and p minus are primes, in fact. Okay, so that's great, because that means that we've shown that this 3 as an ideal is not irreducible in the sense that you can actually factorize it if you enlarge not to numbers but to ideals. Okay, so you factorize that now. Okay, let's just check that when you multiply the p plus and the p minus, you get this 3. Okay, so p plus I've written here is 3, generated by 3 and 1 plus square root minus 5, and p minus is generated by 3 and 1 minus square root of minus 5. So if you multiply them together, okay, it's quite easy to see that it's generated by all the possible products of generators. Okay, so it's generated by 3 times 3, which is 9, and also 3 times 1 plus square root of minus 5, that's 3 plus 3 square root of minus 5, and also this 3 times this 1 minus root minus 5, 3 minus 3 root minus 5, and also by the 1 plus root minus 5 times 1 minus root minus 5, so that's of course 6. Okay, and now you just have to realize that this is actually equal to 3. And why is that? Well, 3 certainly contains this because everything here is a multiple of 3. Okay, but also 3 is inside here, so this also contains that because this contains 9 minus 6, which is 3. Okay, so that tells you that you have equality, and so this ideal 3 actually factorizes as this product of these two prime, in fact, maximal ideals. Okay, so now you have this factorization, but as ideals. Okay, so you might think, oh, that's interesting. What about the other term that we have here, the 2? Turns out that the 2 also you can factorize as well. So how are we going to do that? So firstly, and you might guess this from the example with 3, let's adjoin to 2, 1 plus the square root of minus 5. You can also do 2 and adjoin to that 1 minus square root of minus 5. You get 2 ideals, and it turns out they're the same, because if you look at the difference between this term here and this term here, you'll get twice square root of minus 5, and that's contained in the ideal generated by 2. Okay, so it's quite easy to that. If you have these 2 terms, okay, by subtracting 2 square root of minus 5, you'll get this term as well. So this certainly contains that, and similarly the other way around. Okay, so these 2 are equal. And so again, this ideal generated by 2, you can check it is equal to the product of these 2, but since these are the same, you just say it's the square of the ideal generated by 2 and 1 plus square root of minus 5. Okay, so then let's revisit this factorization that we have over here. Okay, 2 times 3 equals this 1 plus square root minus 5 times 1 minus square root of minus 5. Let's revisit that factorization, but in terms of ideals. So you have the ideal 3 now further factorizes into this ideal. This is the p plus, this ideal which is the p minus, and then the square of this 2 comma 1 plus square root of minus 5. Okay, now what about this one here? Can you also further factorize this? Well, actually there are 2 maximal ideals that contain it, okay, 2 primes that contain it, and we've seen them before. Certainly if I throw in 3 to this as well, you get a bigger ideal, so that's 3 comma 1 plus square root of minus 5. That's already over here, one of them. You can also add in a 2, so you get 2 comma 1 plus square root of minus 5, and we saw that's going to be another prime, okay. And you can do a similar thing with the minus, okay. And what you find now is that both sides are 4 factors, and the 4 factors now actually line up as well. So you've got the 3 comma 1 plus square root of minus 5, okay, occurs here once. This 3 comma 1 minus square root of minus 5 occurs on the other side, but not associated to this one, but to the other one. And the 2 factors are 2 comma 1 plus square root of minus 5. Each of them is distributed across the 2 old factors. So you have one here, and you have the other one, but written as with a minus, is over here. Okay, so it turns out that in this case, actually you've recovered a unique ideal factorization. Okay, you've recovered unique factorization, but in the setting of ideals, so there's more factorization going on. Okay, and it turns out that in this ring, okay, you will have unique factorization. Okay, and this begs the question. Okay, so this was his ideal, is to not look at Kummer's idea was not to look at just numbers themselves. Okay, but to look at the ideals. Okay, and also ideals generated by numbers. And it begs the question, firstly, how often does this unique ideal factorization occur? And then the second question is, well, if it does occur, okay, you have this new version of unique factorization, does it help us? Okay, so there are 2 natural questions that occur in algebraic number theory. And the answer is that yes, they occur often. Okay, this occurs often. In fact, if you have any ring of integers inside a number field, then you will have unique ideal factorization. So you can always apply that idea in terms of ideals. And then the next question is, well, if you have that, well, how does it actually help us? Well, it turns out that you can measure how far a ring of integers is from actually being a unique factorization domain. Okay, so there's a way to measure how far is a general ideal, how far is that away from being an actual principal ideal, so generated by a single element. Okay, and this is measured by a certain group called the class group. Okay, which is a very, very important notion in algebraic number theory. And there's quite a big theorem that will take several videos to explain the proof of, but essentially this class number is actually finite. So the way you measure the difference between being a unique factorization domain, okay, how far you are from being one, is via some finite group. And since this group is small in the sense that it's finite at least, okay, it turns out that a lot of the time, okay, you can actually go back and say, well, it's close enough to being a unique factorization domain that you can apply many of the arguments that you would like to use, such as the one that Lemay used in his attempt at proving Fermat's last theorem. Okay, so just to sum up, what's the key point of Kummer's idea? Is to, rather than just looking at elements, okay, when you look at these rings of integers, maybe things that used to be irreducible are no longer irreducible when you look at them as ideals. So you replace an element with the ideal generated by it, then they sometimes factorize. And the point is that you want to show that in this case you get unique ideal factorization theory, so that's a nice theory that you have. And then you want to say, well, how do you control how far is this unique ideal factorization theory from actual unique factorization of elements? I hope you enjoyed this adventure in pure mathematics.